All right. Good morning, everyone, and welcome to our webcast about autonomous driving, how technology makes cars intelligent. My name is Dominik Friedl. I am Business Development Manager at NTT Global Data Centers, and I have the pleasure to be your host and moderator today. Together with our partners Dell EMC, DSpace, and the Unbelievable Machine Company, we would like to provide you some valuable insights about this topic from different perspectives in the next 60 minutes. And to start right away, let me give you a brief overview of what we do at NTT Global Data Centers. So NTT is a Japanese telecommunications company and known as one of the leading ICT service providers worldwide. Our portfolio spreads from ICT infrastructure, such as submarine cables, co-location data centers, connectivity and cloud, over services like consulting, technical services, managed services, and support for different special topics like intelligent business, intelligent workplace, intelligent cybersecurity, and intelligent infrastructure. So we serve a lot of the Fortune 100 companies. And as I am personally part of the Global Data Centers group, let me give you a brief insight of what we understand of global data centers. So we provide more than 160 data centers in 20 different countries. And that means that we provide the space, the power, the cooling, the connectivity, as well as the security for the IT systems of our customers. And we provide also the direct access to all major cloud providers, to all major interconnection points, and to all major carriers. And with our Technology Experience Lab, we have more than 140 partners that provide more than 80 different use cases in our lab to give our customers and partners the opportunity to test and validate new and interesting solutions of ICT. And when we talk about mobility, there is quite a big disruption going on right now. And as you know, the future of mobility will basically be electrified, shared, connected, and autonomous. And autonomous driving is basically the most trending topic right now in the mobility industry. And there's one interesting number. So by 2050, up to 45% of all vehicles will drive autonomously, but there is quite a way to go until then. So there is a big challenge. And the challenge is that the brain of the autonomous driving, so the advanced driver assistance system, must be trained with masses of data. And so, it has to be really contained continuously, and the data has to be provided and transferred between the car and the training systems. So when we talk about the autonomous driving data flow, it all starts in the car. So the data gets recorded in the vehicles that are driving around, collecting real environment data. Then the data must be offloaded, so really transferred somewhere into a location via a copy station, or also via wireless if that's possible in these data speeds. And then the data for sure must be stored somewhere to collect the data basically in an object storage. And also the data must be processed or pre-processed via AI in the best case to really ensure data quality and also the enrichment to make the data really make sense. And at the end, it gets uploaded into the cloud. So all the major firms and the autonomous mobility providers can really access this data that they were collecting before. But to make it accessible again for the car and really make it useful, it also has to be basically trained. So the ADAS, the autonomous driving system, must be trained and tested in a so-called hardware in the loop or software in the loop simulation. And then the data gets transferred back to the car, so the car gets more intelligent and can drive around on the streets autonomously. And so the one thing that is recording the data is happening for sure on the road, but the other processes have to be happening in somewhere in the data center because it can't be happening in the car. The car is too small for handling such amounts of data. And yeah, so as we in NTT, we provide co-location data centers. We see the data center as a foundation for mobility data. And so there are some requirements on the one hand side technical, but on the other hand side also business requirements towards mobility data. And that's on the one hand side, the data growth. So you need flexible and scalable environments. You need also for hybrid cloud, you need low latency interconnections and direct cloud access. And also for doing the AI and the analytics on the data for enrichment, you also need high power density and strong cooling capabilities. On the business side, there is also a requirement towards the business continuity. So these applications are really mission critical and need to run 24/7, but also security is a big point. So mobility providers registration require IT compliance. That also includes physical security. And then there is also a big regulation going on. So that's also needed and required to have IT processes that are certified via, for example, ISO 27001 and lots of other certifications. And I brought two pictures with me so that I can give you an insight in what data centers look like. So really big data centers are fields of spaces for technology and for cabinets so that data can be stored and processed. And that's, for example, one of our data centers in the Frankfurt region, but we also have data centers like, for example, in Berlin, in Munich, in Zurich, in Vienna, in London, in Johannesburg, and also in the US and India and Asian region. And to start right away with our topic, let me give you a short introduction to our speakers today. So at first we will have Dr. Florian Baumann from Dell EMC talking about the right technology stack for automotive AI. Then we have Bassam Abdelghani from DSpace talking about data replay and validation for autonomous driving. And at the end, we have also Dr. Olivia Luis from the Unbelievable Machine Company talking about active learning, the intelligent parameter selection for hardware in the loop tests in the automotive industry. So let's start with today's talks, and I hand over to Florian.
Thank you very much, Dominic. I will share my screen now, and you should be able to see it in full screen now. So my name is Florian, and I'm working as a CTO focused on automotive and AI at Dell Technologies. I'm part of the Unstructured Data Solutions business unit, and I'm representing two products. The first one is Isilon, our scale-out file system, and the second one is ECS, our object file storage. So today, inside of our session around how technology makes cars intelligent, I'm talking about the right technology stack for automotive AI. And during the next 10 to 12 minutes, I will walk with you through 5 bullet points. The first session focuses on typical challenges that I'm seeing at our automotive customers. I'm talking about typical AD/ADAS facts. I'm introducing you into the development process, also into a data lake architecture on a high level. Then I'm talking about a typical AD/ADAS automotive AI use case. And I'm listing the 10 most demanding solutions that we are receiving from our customers. If I'm talking about AD, I'm talking about autonomous driving. And if I'm talking about ADAS, I'm talking about advanced driver assistance systems. So let's start with the key challenges if we are facing autonomous driving or ADAS in general. So I'm receiving very often challenges around we have to deal with complex test and validation processes, workflow issues, and continuous integration and continuous delivery. So customers would need a fully automated tool chain, as we've also seen on the slides presented by Dominic. So for example, a feedback loop from sending out vehicles to the field to the development and production of algorithms. And we have to deal with a lot of different test and validation processes. Bassam will also introduce you into some of them, like software in the loop and hardware in the loop and vehicle in the loop. So this is a key challenge to create a fully automated tool chain. The second challenge is focused on multi-site and multi-party projects. So very often automotive OEMs and tier ones have their own suppliers, and they have different satellites and sites located everywhere in the world. As also mentioned by Dominic, NTT has data centers everywhere in the world, and our customers, of course, also have different offices and R&D centers everywhere in the world. So it makes sense to implement data management systems and data moving operations to move data from different automotive applications to the other ones. The third challenge is focused on machine learning and deep learning. So product development in that area is an iterative process. We are collecting data, we are training our algorithms, we are testing our algorithms, we are retraining the machine learning algorithm, we are improving the code, and then we are starting from scratch again. So again, we need a fully integrated development tool chain. And the last challenge is focused on data growth. So for example, sensor file needs to be stored on a storage and metadata. And if I'm talking about metadata, I'm talking about, for example, detected objects in scenes should be stored in a database to allow developers to connect to this database in order to locate files. Some typical ADAS facts that I've collected from the automotive industry: companies are collecting up to 5 petabytes of data per week. 1 petabyte is 1,000 terabytes. Customers have around about 40 petabytes on active training and test data sets. Typically, we have to deal with 850 concurrent in and out threads for each small ADAS project, for example, a traffic sign recognition project. Companies are sending up to 100 vehicles to the field in order to record data. And what we are also seeing is that you would need around about 30 different sensors inside of the vehicle to allow them to drive autonomously. If you ask Elon Musk, for example, he will tell you that a Tesla would not need a LiDAR sensor. Most of the other OEMs and tier ones require a LiDAR sensor. So typically you would have up to 15 cameras, 4 to 6 radars, short-range radar, long-range radar, and also ultrasonic sensors and laser scanners on each side of the car. So let me introduce you into the typical development life cycle, and this is quite similar to the one shared by Dominic. So I've divided this process of developing AD and ADAS vehicles into 4 different tasks. The first task focuses on the so-called in-car compute and storage. So companies are sending out vehicles to the field in order to collect data, in order to pre-label data already inside of the vehicle. And they are also starting to connect the vehicle to the infrastructure, to the data lake, in order to integrate the vehicle as a crucial part into the development lifecycle. So the feedback loop, as we've seen it from Dominic's slides. And what is also important is to connect the data through 4G or 5G directly to the infrastructure in order to stream data in real time. The second box focuses on so-called ingest stations or satellites. As we've seen on the previous slides, customers have multi-site deployments in place. They have different R&D offices everywhere in the world. And some typical tasks are offloading the data from the vehicle and ingesting the data into the satellite in order to start the data preparation. So how to identify data that is valuable, how to identify edge cases, how to clean the data, how to prepare the data, and how to compress the data. So most of the tasks are focused on reducing costs, of course, and reduce the amount of needed storage in the data center. The data center, the big one, the centralized compute and storage data lake, is typically consisting of around about 200 petabytes. This is a typical size that we are seeing in the automotive industry, focused on SAE level 4. And some typical tasks are large-scale algorithm training, test and validation processes. And the hardware-in-the-loop rigs are directly connected to this large-scale infrastructure in order to benefit from low latencies and high throughput. And all processes like hardware-in-the-loop, software-in-the-loop are running in this centralized data. And the last box is focused on the data management system. So developers located everywhere in the world are able to log into this infrastructure deployment in order to locate sensor files, in order to improve the performance of their algorithms. Also, they are able to check the progress around the data recordings and the progress around the machine learning process. And they could access the whole infrastructure through dashboards. And they are also able to connect their own proprietary applications through different APIs to the infrastructure. So this data management system is the main tool for developers. Let me quickly introduce you into how an architecture of the centralized data lake could look like. So for example, we have our centralized data lake typically located in a managed co-location at an NTT data center. And this consists of around about hundreds of petabytes, thousands of different CPUs and GPUs. And the data management system is directly connected to this centralized data lake. And now developers located everywhere in the world in so-called satellites or in a remote site could log into this data management system in order to upload data and also in order to locate data, to start and stop compute jobs, to start and stop their machine learning algorithm training and test and validation process. And typically these remote sites are also acting as ingest stations. So let's assume you have a remote site in India and you are sending out some vehicles in India. You could ingest the data locally in India, prepare the data, curate the data, compress the data. After the data is validated and proven to have a good quality, you can ingest this data into the centralized data lake. And then every developer could access this data. Of course, also connected to this centralized data lake is the long-term backup and archive, and then a hybrid cloud deployment infrastructure to also utilize the public cloud providers' compute capabilities or AI services provided by these guys. So the AI use case is brand new. We've released this around about 3 weeks ago, and we've used the Cityscapes dataset, and we've increased the size of this dataset by 557 times. And this benchmark was focused on semantic segmentation. We've used around about 1 petabyte of our Isilon all-flash storage and 64 GPUs. And we've shown that we've been able to push out around about 7,600 images per second through this platform, focused on semantic segmentation. And if we are focusing on object detection and object classification, we've pushed out around about 800 images through this platform. So we've been able to finally push 1.6 million images in less than 4 minutes through this storage and compute infrastructure with a peak throughput of around about 10 gigabytes per second. And we've utilized the GPUs by 96% in average. So we've been able to train a fully semantic object detection framework in less than 4 minutes. And I was quite surprised about this. Let me quickly take a look at the time. So the most demanding solutions are, from my perspective, focused on 10 different tasks. So the first task is focused on data logging and data acquisition. So customers are asking Dell if we could develop data logger and data acquisition solutions with compute and storage included in the vehicle before the production and after the production. So customers also want to apply GPUs for inferencing purposes inside of the vehicle. The second bullet point focuses on Hill reference architectures, for example, with hardware provided by DSpace, The second solution focuses on public cloud hardware in the loop testing, and I'm mentioning in both directions because there are two types of companies. The first type of company wants to move data into the public cloud in order to utilize compute out of the public cloud. And the second type of company focuses on how to copy or move data out of the public cloud into the physical hardware on-premise in order to benefit from low latencies and high throughput. So public cloud testing in both directions. The fourth solution focuses on synthetic scenario generation and also reference architectures in order to, for example, synthetically generate corner cases or scenarios that are too dangerous to record in the real life. The fifth point focuses on data management, metadata management, and how to automatically ingest or offload the data from the vehicle and to ingest the data into the infrastructure. The sixth point focuses on data movement, so how to physically move data from, for example, US to Europe. Huge amounts of data, we are talking about tens of petabytes of data, and also on how to compress this data. And the seventh point focuses on so-called data science platforms. We've seen the progress of ADAS development on the previous slides, and a lot of customers are requesting an end-to-end platform in order to develop ADAS and AD solutions, from ingesting data to the production of algorithms. Point number 8 focuses on real-time streaming, how to stream data in real time from the vehicle into the infrastructure, also focus on connected vehicles. And point number 9 focuses on cloud-native app development, how to move workloads seamlessly into the public cloud, how to create a Kubernetes-based application development environment, how to utilize Docker containers and the cloud-native landscape. So from my perspective, these 9 points are the most demanding solutions, and a lot of customers are requesting support for these solutions. So let me come to the end and reach out to me through LinkedIn, through mail, or give me a call if you need some information, and I'm handing over to Dominic in order to answer your questions. Thank you very much.
Perfect. Thank you, Florian. That was really interesting. I'm looking into the chat and it's quite wide. So there's white space, no questions so far. So yeah, if anyone has any questions, please type them into the chat so Florian can give you the answers. Otherwise, we can very slowly already switch to the next speaker. All right. I think, Florian, you will be around, right? So if there are coming up questions afterwards, you can also answer them directly in the chat.
Of course. Thank you very much.
Perfect. Thanks. So over to Bassam.
Okay, so let me share my screen. Are you able to see it?
Yes, we can.
Okay, great. So thank you, first of all, Dominic and NTT for having us today. And yeah, good morning, everyone. And my name is Bassam Abdelghani from DSpace, from the product management team in automotive driving and software solutions. And yeah, automated driving, this is a challenge that we are all talking about today. We all have this vision, sitting in the car, maybe using the extra time for reading, exploring extra activities, or yeah, other people would say the advantages in the reduction of accidents. Between 94 and 98% of accidents are caused by human errors, which can be eliminated by autonomy or autonomous vehicles level 4 and 5. And on the other hand, there is, of course, the financial benefits. Maybe the huge park places that are in the city center that will be freed when less number of vehicles are on the roads, or maybe the other business models that will be generated by autonomous vehicles. All this is good, and all this is a vision that I believe that all of us share. However, achieving this is quite complex. So if we take a look on how the existing or till the near previous history, how the simple vehicle was created. So you have the driver who is basically controlling all the functionalities. He does the perception, he does the trajectory planning, and at the end, you have only in the vehicle the control of these functions. So you will have the motor control maybe for the engine, you will have the actuation of the brakes, and so on. This was good, but it's not sufficient for autonomy. And that's why the complexity comes in. So you will have additional software components added into your vehicle. Basically, you will have some sensors. I believe that Florian actually described it very well with the different sensors that are in the vehicle, ranging from lidar, camera, radar, and so on, and the huge amount of data that they generate. And these sensors will then, and the output of these sensors will have to be processed. So it will be done some kind of data fusion, detection of the different sensor outputs, detection of the objects on the roads. If they are static objects, maybe they are moving objects, we will have to do some scene understanding to detect this. And then we will have to predict the output or the next movement of these objects. And at the end remains the classical components that were existing in the previous vehicle, which are basically the control, or in this case indicated as the motion control. And we see here this separation. So the actuation and the control that is held previously and developed till now, this will remain the same. So we will depend here on the existing classical model-based design, development, and validation, which is quite familiar in all the automotive world. However, when we take a look at the other functions, ranging from perception, fusion, and scene understanding, they are mostly developed in other tool chains. So if we are talking about ADAS, advanced driving assistance systems, ranging from level 1 till 2, 3 maybe, they maybe are developed in in C++ environment and so on. But if we go to higher autonomy level, we see that these functions are basically artificial intelligence functions due to the complexity of the scenarios that they have to drive in. And to generate these functions and to develop and validate these functions, a huge amount of data is required. We are talking about petabytes of data that has to be collected in the field as real data, as real world data, to achieve the most of the range of the operational design domain of these functionalities. However, this is not sufficient. So you will not have, as also Florian mentioned, you will not have the critical scenarios in the real world. The critical scenarios will have to be generated synthetically in simulation environment to add on the real world data. And to achieve and to overcome this challenge, we in DSpace have new product portfolio ranging from explicitly for the data-driven development and validation toolchain and solutions. So we have our solutions for data logging, ranging from our Otera Autobox for in-vehicle data logging, which can be supported by GPUs to put in-vehicle processing or pre-processing of the data, maybe some kind of first-level annotation of the objects. And we in cooperation with our subsidiary Understand AI, we are able to do data enrichment, which is basically labeling the data that is being recorded in vehicle and extracting ground truth data out of it. Why? So that at the end, this data can be valid for the training of the artificial intelligence and also for the validation of it. And we also have the functionality to generate scenario out of this measured data, which is quite interesting, as when the real world scenario that is being driven and recorded is mirrored in a simulation environment, I am able to variate a lot of parameters in these scenarios. So maybe instead of the car behind me or near me moving with 20 kilometers per hour, I would be able to move it with 30 kilometers per hour. And this brings us to the scenario-based testing, as I am able in the synthetic simulation change all the parameters, all the driving parameters and environment parameters to achieve higher coverage of my operational design domain. And of course, that being said, we need high fidelity in the outputs of our simulation. And this is achieved with our sensor realistic simulation, as we use physical based models to generate output that is quite similar to the real world data. However, of course, nothing can be achieved by in the level of reality that is in the real world, because otherwise we could be then living in the simulation. But this is another topic. And of course, all of this has to be scalable, which can be done then simulated in NTT data centers, which can be simulated in cloud and all over the world. And the backbone of all of this is, of course, a data management and test system. However, that's all being said, we here have the data replay, which is basically where 80 to 90% of the validation of the perception and fusion functions happens. And today I will try to walk you through this data replay validation system. That being said, what is actually the challenge with data replay? At the end, I am only replaying the data as it is, some would say. Well, that's a good idea. However, we have this system under test or device under test. That's ADAS, AD, central control unit maybe. If we see what the inputs of such a control unit are, we will see that they are fed with data in vehicle normally, with camera, radar, lidar, multiple sensor. And in addition to that, they are fed with Ethernet, maybe some IP, CAN, FlexRay in some cases. And all of these sensors, all of these inputs are heterogeneous, of course, and they have to come in the right timing. So getting the vehicle out of the loop and ingesting the recorded data directly to the system under test, we will have to maintain high accuracy in the replay of this heterogeneous plane. All the sensors, all the inputs have to be synchronized. Maybe in some cases regarding the network and bus data, maybe I, as a producer of this system under test, I want to test the security stack of these buses. So I have some kind of security on-chip protocol that I want to test. I have IPsec protocol, and all of this has to be calculated in real time during the replay process. And of course, you do not have to test like with one system or two systems. You have to be very scalable. So you have to replay data in a huge manner to test millions and thousands of kilometers of driven kilometers. For that, we in DSpace built a very modular solution to overcome this challenge. So we begin with replay component that is basically able to parse and stream the different data, the heterogeneous data streams, and going to the sensor data interface, which is dedicated only for the raw sensor data that is being ingested to the system under test. And parallel to that, we have our bus data interface for the other network data, basically. And we use then our RTMap solution, which is responsible for the streaming of the data. Our environment sensor interface unit, which is an FPGA-based system that is able to replay up to 12 sensors with a single unit. And of course, we have our famous Scalexio system, which offers low jitter in replaying the bus data. And of course, it offers also the validation and real-time data enrichment with the security features for the bus protocols. In the software, we have also RTMaps, and then we have the virtual ECU EC unit, and Veils, our realistic simulation platform Veils for the virtual ECU simulation and for the data preparation, bus data preparation to the virtual ECU. That is good. However, for the scalability, we need some kind of test management framework. And that covers both of them, the data replay hardware, HIL, or software and SIL. In this case, we have our in-tempora validation suite for the test management. And I'll go through these solutions quite quickly to show what advantages do we have. So when we check about the software validation, we will see that we have here two different use cases. If the customer, and if you are in the beginning of the development of your protocol, of your functions for perception and sensor fusion, you'd be probably in a prototyping framework, whether it's ADTF, ROS, maybe RTMaps itself, and your software components will have to be connected to the data. In this case, we offer this easy interface between our replay solution and your development framework. It doesn't matter what kind of framework are you using, we are able to synchronously send the data in the right time stamping to your function. And taking this into consideration, and when you go step for step towards production, maybe you are utilizing then adaptive autos are adaptive, or then in this case, we are able to realistically simulate the buses, the vehicle buses, whether it's Ethernet, CAN, and so on. And we also are able to realistically simulate your virtual ECU. And of course, the advantage that you will have here is that you will be able to have high confidence in the system and in the test itself. So you will be able to test more software layers prior to deployment on target. And of course, all of our products are very scalable, and they are basically all Docker containerized, so they can be integrated not only in our test management framework, but in your test management framework if you have one. And going into the direction of hardware replay, we have here the advantage of this separation, as we can add multiple of these systems, maybe as a sensor interface or the Scalexios, to adapt for the inputs that you have. So if you have quite simple, maybe a sensor component, we can integrate this directly through, we can test 12, up to 12 of the sensor components with one system. But if you have complex ADAS or AD platform that needs quite number of sensors, we can scale, for example, two environment sensor interfaces, multiple Scalexios, and all of the system architecture will be synchronized with generalized precision time protocol to ensure that the data are sent to your device under test in the right time with the right quality. And maybe a niche case that we get sometimes from customers is when we hear that, okay, I started recording maybe a little bit too late. Maybe I started recording when my when my vehicle is on 20 kilometers per hour. How can I adapt for this from 0 to 20 kilometers per hour phase? In this case, we are able to utilize the same architecture and the same hardware to ingest rest bus simulation data, and maybe also sensor realistic simulation data to ramp up the device under test to the start of the recorded data phase. So at the end, you will not have any kind of failure warning get from your device under test that you are starting with the faulty numbers or faulty status. And with the enrichment and recalculation of the enrichment and time information on the Scalexio system, you are not able only to avoid replay attacks on your device under test, but you are able to test the full software stack of your device under test, whether it's the component itself or the security protocols. This is an advantage in our system. Okay, then speaking of which, hardware replay, software replay, how can I actually manage all of that? So in cooperation with our partner company, Intumbora, we have this tool, which is called IVS. It's basically a cloud-based data management system for which you are able to basically record the data, maybe with the Otera system, our Otera systems. And you can start with annotation, in-vehicle annotation with metadata. You are able to ingest the data on Dell hardware, for example, in NTT data centers, for example, and then the data can be distributed all over the world. You are able to access this data and search it through the through the metadata. So you can, for example, find out what kind. You search for roundabout with a weather night, or like in a nighty weather or with cloudy environment, and then you get the data directly. You are able to export like samples of these data sets, of course, and then you can do the Docker, like you can do the algorithm development locally, and then you can upload the whole algorithm to the cloud or to the data center, for which you can scalably test your algorithm across all the data sets. And of course, at the end, you are able to do batch post-processing, and one of the post-processing algorithms that you are doing is basically data replay tests, whether it's on Silk cluster or data replay Hill systems. Yes, so at the end, the system is agnostic to data formats and middleware, post-processing tools, and you are able to achieve all your data processing in it. So that being said, last slide for me, I would say that as a takeaway, we in this space, we offer comprehensive solution for data replay and big data management. And we will walk through the development and validation process with you, whether starting from software and hardware, software validation, and then to hardware validation. And all of our systems are basically installable on your data center, and of course, in co-location data centers, which NTT is one of the best options for it. That's it from my side.
All right, thanks a lot for that quite deep insight. It was really interesting, and there are no questions in the chat, so we can directly switch over to Olivia from the Unbelievable Machine Company.
Okay, then let me also share my screen.
We can see it.
Can you see it? Perfect. Okay, then I will start the last presentation. I hope you're still all there and awake. So I myself am Olivia Luis. I've been with the Unbelievable Machine Company now for 2.5 years. My background is in physics, and then I did a PhD in neuroscience, and then moved on to data science. I've been a data scientist in 2 companies before the Unbelievable Machine Company, then joined there as a data scientist as well, and then took over the team lead role a year ago. So been in that space for quite some time. Today, I want to talk about active learning and how that can help you to reduce the amounts of data you're collecting. As Yoda is saying here, too much data you have, clean up you must. So I want to show you how you know that process can be helped or done more efficiently. Right, then to move on. Just a quick overview of the company and where we're located. So we were founded in 2008, based mainly in Berlin. We also have offices in Frankfurt and Vienna, so in the German-speaking realm. And then we joined the Base Farm group in 2017, basically expanding also to the Nordics, here shown in blue, and then joined the Orange Group in 2018, expanding even further in size. Just to give you an overview how we fit in also with eShelter. So as a part of the NTT group is basically our data center provider in Berlin and Frankfurt, where we offer classic hosting or co-location as managed service provider. Just a quick overview of what we offer, what we do. So we basically offer services along the entire data lifecycle. So from big data, cloud, security, we have specialized teams for data science, data engineering, operations. So from really the intelligence to the hosting, everything is offered within and today I want to dive deeper into data science. We offer different types of services within the realm of data science, also within different industries. Automotive is one of them. For example, predictive analytics use case that we have done for a big automotive client is on AWS. We set up, like a pipeline basically to retrain algorithms every night. And in this specific case, we've set up an algorithm that predicts seat heating configurations to make the life of the end user a bit nicer and more comfortable. However, today I want to speak about a different sector, the robotic process automation, RPA, and want to give you a specific example of hardware in the loop tests for that one. So to start, I want to ask the question if one can collect too much data. I already gave it away in the beginning. The answer is yes. So why is that? We've heard also in the previous talks and everywhere you hear more data is better. You need a lot of data for machine learning algorithms and for training. Yes, that is true, but you also need the right kind of data. So you could potentially reduce the amount of data that you are collecting in the first place to then also save storage space. You know, you have to maintain data, you have to govern data, you have to clean data. So all that is a tremendous amount of work. And if you can, that should be reduced to a minimum. A specific use case that we have realized for a big automotive client within Germany is looking at hardware in the loop tests. So you have a little sketch on the right where you have the connection between the control unit and the hardware in the loop simulator. Why do we say in the loop? Is because we have the connection between the control unit and the simulator. We give signals to the simulator and then give up parameters back to the control unit. And then form a loop between the two, which is then your hardware in the loop. The scenario that we looked at is automated braking. So you have the scenario that you have two vehicles driving where one vehicle in front is sharing into the space of the hind vehicle, then expecting the hind vehicle to brake if the distance and the velocity is within a certain range to then assist the driver of the hind vehicle. So the question is, how much data could you collect, or what data should you collect? So if you're looking at this scenario, you have a 2D space. You're looking at the distance between the vehicles and the velocity. So I've sketched a few dots here just to show you. I mean, you could have certain spacing and say, okay, I test every 5 meters or so. And also maybe velocity in certain steps, or you could go everywhere in between as well and test everything in that space. So what makes sense and where should you test? So that really depends on the purpose you're collecting the data with. So in this scenario, I said, okay, we're looking at emergency braking sensors. And the question of our client was to find out where did the sensor not activate. So basically, where's this boundary between the sensor activating and not activating, which is this boundary shown here between the kind of brownish area and the white area. We put a bit of noise onto it to make it a bit more complicated and ensure the scenario working also when the data is not perfect. So if you look at this, it becomes very clear that there's this bisecting line. So there's this line between the two spaces of braking and non-braking, and you might already guess, maybe I shouldn't or don't have to necessarily test in certain areas where I know the sensor won't activate or nothing will happen because the vehicles are way too far apart or they're driving very, very slowly. We're basically just interested in the area between the two colored spaces and maybe not test in the bottom left corner. So what is the traditional approach and what did our client do before we came into the play? So the naive approach is to test randomly across the space and then train a model to find this braking, non-braking boundary, use that information, test randomly again, and so on. So have this loop of basically testing randomly and finding out with more and more data, coming closer and closer to this line that you're looking for. I have a short video here what this would look like. So these lines are basically the model finding the boundary. And you see that the model becomes better and better in finding the boundary when more and more dots coming in. The blue dots are the tests. The background is basically the ground truth if you would test everything. So you see more and more tests coming in. The boundary is found slowly better and better. But this takes quite a long time. You can see that we need more and more dots and we're still not perfect. And these tests are done not in parallel, they're done after one another. So you can imagine this taking quite a long time when these tests are done in real time. So now let's consider a different scenario. This is the active learning approach, the one that we implemented. You also start testing randomly in this case. And then you train a model, so the same approach as before. But then the next point is, okay, now you have a model that can tell you where the model is most uncertain. And then you cannot test randomly in the next round. You can then test more intelligently and test somewhere where the model isn't so sure. So this approach will look a bit different. So we start random, then the model becomes smarter and finds that boundary. And you can see these blue dots start appearing more and more around the boundary because the model might test somewhere in the white space and gets the result back, okay, the braking was not activated. Then it might test somewhere on the left in the brown space where the braking was activated. So the model knows that the boundary must be somewhere in between. So the next time it can test somewhere in between. And you can see very, very quickly test parameters are selected around the boundary of interest and the model finds that boundary much quicker. If we speed this process up, you can see an overview after several tests. You can see on the left, you have testing everywhere at random. And on the right, you can see very quickly the model zoomed into that boundary and started testing around the boundary of interest. And summing this up, you can reduce tests. So if you have 5,000 tests in a random scenario to get to a 95% certainty of where your boundary is and how well your braking is functioning, you can reduce, or we reduced in this case, testing tenfold. So we were able with only 500 tests to get to the same certainty of that boundary. What does that mean in testing time? So as I said, tests are done not in parallel, they're done after one another, and one test takes about 3 minutes. So these are done in real time, even though they're simulated. That means if we save tenfold of tests in this case, we save 9.5 days of pure testing time. So that's a huge achievement in reduction of tests. So this is a very specific example. This can also, or active learning can also be used or utilized within different scenarios. You can imagine not only a 2-dimensional space, as I showed you now, but a high-dimensional space. We've done this, for example, for parking, where you have on top of these parameters that we've looked at here, we also have angles and other parameters. We did this for 5D in that case, which also worked fine. So basically everywhere where you have a lot of labor, manual labor, and a lot of data storage involved, it makes sense to reduce this amount of work. This could also be labeling of data. This is done often manually. So if you have an algorithm that basically only lets you label the images where it's uncertain about the component that you're looking for, it will ask a human agent, for example, to label that image, but where the algorithm is more certain and won't bother the human, but will move on. So these process automation options using active learning are very useful in reducing amounts of work. Okay, then I want to finish with that. Feel free to contact me anytime or our sales team. Yeah, I'm happy to answer any questions now if there are any in the chat. Thank you very much.
Thanks a lot. That was really interesting. And there's also one question that came up in the chat. So Dennis is asking, is there any way to watch a live demo or of not only an autonomous driving car, but also of the dashboards and how the information is processed, collected, viewed, and analyzed?
So would this question go to me, or because it's not very specific to this scenario, or to any of the other speakers?
That's a good question. I think it came in your talk, but probably it refers to the talk of Bassam. I'm not sure.
Yeah, I think so too.
So yes, sure. Maybe we can arrange this and afterwards a small demo to show how are we logging the data in vehicle and what kind of in vehicle processing are we doing. This can be arranged.
Okay, perfect. All right. So if there are no more questions coming up, I think we're quite in time and 3 minutes early. I would like to thank all the speakers for today's insight in their topics. So it was quite interesting, and I hope you enjoyed the talks. If you're interested in any more materials, please contact us directly, and we will also send around a follow-up email where you can have access to the recording and also to the shared files of today's webcast. In that regard, thank you everyone for attending, and a special thanks to all the speakers, and have a great day.